In this video, I will spend a few minutes discussing energy in an LC circuit. So in this circuit, I have a capacitor and I have an inductor, and that's the only thing that I have. There is no resistor, and I have initially charged the capacitor so that the charge on the capacitor goes up and down, and the same thing happens for the inductor with its current. I know that the charge on the capacitor as a function of time is given by this expression. The current in the inductor is given by this expression, and where omega is 1 over the square root of LC, and phi naught is just the initial phase of the current and the charge. Now I'll just make a note that this is the charge on the capacitor, and this is the current in the inductor. Now I'm going to start with the inductor. I know that whenever there is a current flowing in the inductor, there is energy stored in the magnetic field that the inductor creates. So the expression for the potential energy of the inductor, this is magnetic potential energy, is given by 1/2 the self-inductance times I squared. Now I'm going to use this since I know what the current is in the inductor, and I will just square everything. So the minus will go away, then I will have omega squared Q naught squared and the sine squared of omega t plus phi naught. Now if you see here, 1/2 is a constant, the self-inductance is a constant, omega is a constant, Q naught is a constant. So all of these are just going to be a single number at the end. But I have the sine squared of omega t plus phi naught. Now phi naught is a constant, omega is a constant, t depends on time, t is time. So what this expression is showing me is that the magnetic potential energy of the inductor depends on time. And it also shows me, because here I have sine, the sine squared, it also shows me that this quantity, the magnetic potential energy, goes up and down, up and down, up and down. It is essentially oscillating between 0 and its maximum value forever in this circuit. Now this is what I get for the magnetic potential energy of the inductor, and for the electric potential energy stored in the capacitor, in the electric field of the capacitor. That expression, we did it when we discussed capacitors, is 1/2 C delta V squared. Now I need to do some kind of transformation here because I have C and delta V, but what I know about the capacitor here is the charge. And I also know the definition of the capacitance. So delta V is Q over C, and I can use that here. 1/2 the capacitance, the charge squared, divided by the capacitance squared, and this C with the 2 will go away. So what I have is 1/2 Q squared divided by C. Now what I'm going to do, since I have the charge on the capacitor, I will use it here, and it will be 1/2 1 over C, and it will be Q naught squared times cosine squared of omega t plus phi naught. Alright, so this is similarly the electric potential energy stored in the capacitor, and there is a time dependence since I have cosine squared of omega t. Now again, 1/2 1 over C and Q naught squared, those are constants. So in a similar fashion, the electric potential energy stored in the capacitor goes up and down up and down forever, that this energy oscillates essentially between 0 and its maximum value. Now, I'm going to make a note. So this is, okay, EP, the electric potential energy, is stored in the electric field of the capacitor, and the magnetic potential energy of the inductor is stored in the magnetic field that the inductor creates. All right. Now I'm going to do one last thing. I'm going to add these two potential energies. So I'll take the magnetic potential energy that depends on time of the inductor plus the one of the capacitor that also depends on time. Let's see. So it's going to be 1/2 L omega squared Q naught squared sine squared omega t plus phi naught plus 1/2 1/c Q naught squared cosine squared omega t plus phi naught. Now, one thing that I will do, since I know that omega is equal to 1 over the square root of LC, omega squared will be simply 1/LC. Okay, so instead of using omega squared, I will just use 1/LC. 1/LC. But here it is. This L with this L cancels out. And if you take a look, the constant here is exactly the same as the constant there. And that allows me to take it out as a common factor. So it is 1/2 Q naught squared over C. And what I have in the bracket then is the sine squared omega t plus phi naught plus cosine squared omega t plus phi naught. But this is a sine squared plus cosine squared. I know that this is always true, always equal to 1, because the two arguments of the sine and the cosine squared, they are the same. So really, this is equal to 1/2 Q naught squared over C. This is a constant. Okay, this here is a constant. It does not depend on time. The sum of the two potential energies in the circuit, or if you want, the total potential energy in the circuit, remains a constant and is independent of the time. This is an important result. Why is that the case? Well, the inductor never loses any energy. The capacitor never loses any energy. If you will lose energy, it will have to come from a resistor in the circuit. I don't have any resistor in this particular circuit. Okay, this is an LC circuit. There is no R. So long as there is no R, no resistance, your circuit will never lose energy. The energy will always stay there, and it will be equal to this number. Now, this is theoretical. Okay, if you actually make an LC circuit, do you not have any resistance? You do have some resistance. Remember, even using the wires that we typically use in circuits, there is a very small potential difference across your wires. So in theory, we treat them as to be ideal wires that give you a delta V of 0, potential difference of 0. In reality, there is a small potential difference across the wires that we use to make the circuit. So you will always, when you construct an LC circuit, yes, you will lose some energy. It will be a little bit, but you will be losing it as time goes by. Now, in theory, where we assume there is exactly no resistance, the sum of the two potential energies stays constant. Now, it is interesting to take a look at this quantity. I have 1/2 Q naught squared over C. But if you see, this is exactly what the maximum value of the electric potential energy stored in the capacitor is. Okay, which means when the capacitor is fully charged and there is no current flowing in the inductor, all the energy is in the capacitor. Now you can also show that, okay, so the sum of the two energies, EP, so what I just showed is that this is equal to 1/2 Q naught squared over C, but we can also show that this is equal to 1/2 L omega squared Q naught squared. And I can do that simply by saying omega squared is 1 over LC. So those two are equal. But this is, okay, let me make some notes. So this is the maximum potential energy stored in the capacitor. And this is the maximum magnetic potential energy stored in the inductor. Using everything that I've said so far, the magnetic potential energy in the inductor oscillates between 0 and the maximum value. The potential energy stored in the capacitor oscillates between 0 and its maximum value. The sum of the two stays constant, and because when one of them is maximum, the other one is 0, and the other way around, the sum of the two potential energies is equal to either the maximum electric potential energy or the maximum magnetic potential energy in the LC circuit.